So, dear students, we will continue with our yesterday's discussion on amplitude modulation. How do we generate AM signal? And today we will also talk about the detection of AM signal. Okay. So yesterday we had talked about the generation of SSB signal. I had told you that the most simple method to generate SSB signal is the use of filter method. So by using filter, we can filter out the undesired sideband and we can allow the desired sideband. So that's the most simple and the trivial solution to have single sideband signal. And we have discussed this thing in detail in the yesterday's class as well. Okay, so I hope all of you have understood this. So for filter method, first what we will do, we will generate single sideband double sideband suppressed carrier signal by using balance modulator. And then once we have removed the carrier, then we will be using sideband suppression filter. As a result, we get either the lower sideband or the upper sideband, whatever is our requirement. Fine. And we have already talked about the power saving as well as bandwidth saving, which is available during the generation of SSB signal. So on your slide, the power which is consumed in single sideband modulation has been shown. Okay, next. So this is the method that we have to discuss today for a generation of single sideband signal. If you look at the method that we have discussed in the previous slide, there mainly what has been used, we have used sideband suppression filter. Okay, so with the help of filter, we have removed one of the sidebands. And students, I have talked about filters a lot in the previous semester as well. We know that ideal filters are not possible to be designed. So there are some, additional components available, and because of non-ideally filter characteristic. So that's why we try to do away with filter as far as possible. Apart from that, filters, they are not that easy to basically realize in the desired fashion. Okay, so when we use filter, we look for some other methods also with the help of which we can do our desired job. Okay, so that's why, like here also, apart from using filter method, we are looking into some other method that can give us single sideband signal. Okay, and your phase shift method is a method in that direction only. Okay. So in phase shift method, what do we use? Obviously, we will be using balanced modulators, and this method avoids filters. So that is the biggest advantage of phase shift method. And in phase shift method, what we use two balanced modulators. Okay. So I have shown you the block diagram of the phase shift method. First, we will have a brief look at the block diagram, and then mathematically, we will prove the operation of phase shift method. Fine. So you can see here that we have balance modulator 1. So at the input of balance modulator 1, what we have, 1 as the modulating signal direct. Okay. And the carrier signal is not applied directly to the balance modulator 1. It is applied after 90-degree phase shift. Okay. So you can say here that in the balance modulator 1, modulating signal goes as it is, and the carrier goes after 90-degree phase shift. Similarly, in the balance modulator M2, your carrier signal goes as it is, whereas your modulating signal, it goes after 90-degree phase shift. Fine. So it's the, vice versa. In case of balance modulator 1, modulating signal as it is, carrier is phase shifted by 90, whereas in case of balance modulator 2, your modulating signal is phase shifted and carrier is as it is. So once we have obtained the outputs of the two balance modulators, then we can either add or subtract them. And finally, here at this point we get the SSB signal, that is your single sideband signal. So I think a very straightforward block diagram is there for your phase shift method. So we will prove this thing that the output of this phase shift method gives us single sideband signal mathematically. Okay, so with the help of mathematical expression, now we will see to it. So let us move forward. So now let us see. So this is the circuit of our phase shift method, which uses two balance modulator. So first, let us look at balance modulator 1. Okay, so before we move to balance modulator 1, we already know that balance modulator works as a multiplier. So in multiplier, we have two signals. One is your modulating signal and another is our carrier. Okay, so our modulating signal is represented as capital VM sine omega mt. Okay, that is your message signal, and your carrier is represented as VC sine omega ct. Fine. And you all know, you are well aware of mathematical concept. If we provide 90-degree phase shift, okay, then your sine becomes cosine. So sine omega mt, it becomes cosine of omega mt, and your sine omega ct, it becomes cosine of omega ct. Okay, so this is how your phase shift works. So after phase shift, your modulating signal becomes Vm cos omega mt and carrier becomes Vc cos omega c. Okay, now with this thing, now we move forward and we concentrate on balance modulator 1. We know the working of balance modulator mathematically as well, as we saw in the previous class. So balance modulator, what it does, it multiplies the two inputs. And what are the two inputs in balance modulator 1? The two inputs are your modulating signal and carrier, which is 90-degree phase shift. Okay, so let us see. So your modulating signal as it is. So where is our modulating signal? It is Vm and then sine omega mt. This is our modulating signal. Okay, and what about our carrier part? Our carrier is Vc cos omega ct. Why it is cos omega ct? Because we have done 90-degree phase shift to the carrier. And we already know that balance modulator multiplies the two inputs. So it is multiplied. So the output of balance modulator is straightforward. Balance modulator 1 is straightforward Vm Vc sine omega mt cos omega ct. Okay, so now we know the trigonometric relation. We have this expression as Vm and Vc are constants. So this term sine omega mt sine omega ct can be shown as sine A sine B. Okay, so multiplication of two sine functions. So it gives us 1 by 2 sine A plus B plus sine A minus B. Okay, so if we apply that trigonometric identity, we get Vm Vc by 2, then sine omega c plus omega mt and sine omega c minus omega mt. So the output of balance modulator 1 gives us this expression. So Vm Vc by 2 is common outside, and inside we have sine of omega c plus omega mt and sine of omega c minus omega mt. So next we move to balance modulator 2. So in the balance modulator 2, your modulating signal is 90-degree phase shifted. Means your modulating signal will be Vm, then cosine of omega mt. Okay, and your carrier is provided as it is. So means your carrier is Vc sine omega c. And again, the two signals are multiplied and we apply the same entity. Then what do we get? We get Vm Vc by 2 multiplied sine of omega c plus omega mt minus sine of omega c minus omega mt. Notice the difference in the sign. In the output of balance modulator, we have plus sign in the two terms, whereas in the balance modulator 2, we have minus sign in between the two terms. Okay, so now you carefully observe here what we want. We want single sideband. Okay, we want either the upper sideband or the lower sideband. You concentrate on these two terms. If we want upper sideband means this term and this term. This will be obtained if you add these terms together, because if you add them, then this lower sideband will be cancelled. If you add them, simply mathematically add. So by adding them, we get upper sideband, the left hand side. Okay, and on the other hand side, if we want lower sideband, in that case, we want to preserve these two terms, omega c minus omega mt. Okay, so but there is a minus sign. So what we will do, we will subtract them. So if we subtract them, this term and this term will be cancelled. This minus minus will become plus, and we will get this term, VMVC sine of omega c minus omega m into t. Okay, so this is our lower sideband, and this is our upper sideband. So whatever we want, we can obtain that sideband. If we want upper sideband, we will add the two signals or the outputs of two balanced modulator. If we want lower sideband, we will subtract. So you can very easily understand here that just by mathematically manipulating and realizing those mathematical expression correspondingly by block diagram, we can obtain or we can generate a single sideband signal. And we have not used any filter anywhere, so you can very easily see that we could generate single sideband signal without any problem here. Okay, so this was the phase shift method for generation of single sideband signal. Hope all of you have clearly understood this thing. Once you have clearly understood the concept of balanced modulator, then phase shift method is very, very easy to understand. Okay, so though I'm saying that phase shift method is perfect method, it avoids filter, it uses two balanced modulator, but there are some disadvantages associated with the phase shift method for single sideband signal generation. So let us see to that, and then in order to remove those disadvantages, we will move to some other method that will be generated out of your phase shift method. Okay, so now let us see to that. So first, let us see the advantages of phase shift method. The first advantage of phase shift method is we can easily generate our SSB signal at any frequency. That's the beauty, because your filters, they do not provide desirable characteristic at all the frequencies. Whereas in case of your phase shift method, there was no requirement of the filter, and we can generate single sideband signal at any frequency. Apart from that, the phase shift method allows us the use of low audio frequency for generation of single sideband signal. Okay, so means at lower range of audio frequency, the phase shift method works in a nice manner. Okay, so these are the advantages. Whereas the main disadvantage of phase shift method is the disadvantage is the phase shift network. Okay, so what we have done in our SSB signal generation using phase shift method, we have used this. We have used 90-degree phase shifter for carrier, and we have used 90-degree phase shifter for modulating signal. When we use phase shifter for single frequency, there is no problem at all. Okay, but see, students, try to understand, we have two types of signal. One is modulating signal and another is carrier signal. Okay, and our modulating signal is our information signal. Okay, and if we correlate this information signal with practical signal, we see, what do you get at the output of the receiver? You get audio signal. See, our message signal or information signal is some audio signal. Obviously, either it will be audio signal or it will be your video signal. Okay, so here we are using audio signal. Okay, so we have audio signal as our modulating signal, and we have a carrier signal for carrying this audio signal from one place to another place. Okay, now we already know what is carrier. Carrier is a high frequency, you can say sinusoidal frequency component. Now, what is audio signal? Does audio contain a single frequency? No. We know that what is the frequency range of audio signal? The frequency range of audio signal is from, yes. Okay, first let us discuss what is the difference between audio and speech. Audio and speech. So audio means whatever we can hear through our ears, that is called audio signal. And speech signal is what we can speak. We can generate through our vocal cords. Okay, so your audio signal range is from 20 hertz to 20 kilohertz, that you very well fully know. 20 hertz to 20 kilohertz. So your audio signal range is between these frequencies. So it consists of range of frequencies. It neither consists of a single frequency. This is our audio signal. And your speech signal, it normally concentrates from 300 hertz, okay, to 3400 hertz. Okay, so that means 3.4 kilohertz. See, we can listen through our ears the frequencies from 20 hertz to 20 kilohertz, whereas we can speak out from our vocal cords just a frequency range from 300 hertz to 3.4 kilohertz. Okay, so if I talk about the frequency range for speech signal, it is just 3.1 kilohertz, means the highest frequency minus the lowest frequency. So your speech signal has this much bandwidth, you can say 3.1 kilohertz, whereas your audio signal has around 20 kilohertz, you can say bandwidth range. Fine. So when I say that audio frequency, it means this much. When I say speech, this much. Okay, so in most of the cases, when we talk of modulating signal, okay, for the sake of simplicity, at most of the places, your modulating signal will be audio signal. Okay, so whenever we say modulating signal or our audio signal, it means it is having certain ranges of frequency. Fine. So it means when we talk about 90-degree phase shift, it means we do not have single frequency to phase shift. We have so many frequencies for which we need to phase shift for modulating signal, whereas for the carrier, we have only one frequency to phase shift. So shifting the phase of so many frequencies at a single value of the phase shift, say that is 90 degree, it's not that easy. It's quite difficult. So that's why whenever we need to use phase shift network over range of frequencies, then it is a difficult task. So that is the disadvantage of phase shift method, that there is a requirement of audio frequencies phase shift network to operate over large range of frequencies. Okay, so that's why we move to third method. So in third method, what we will try to do, we will try to use a single frequency for phase shifting instead of having multiple frequencies for shifting. Okay, so that's the main idea behind the development of third method. I hope all of you have understood this thing. Fine. So students, now we move to third method. So in third method, what are the major changes that we have to incorporate? First thing is, in the third method, we'll be using 4 balanced modulators. In phase shift method, we use 2 balanced modulators. So in third method, we use 4. That is one point. Second thing is that instead of phase shifting the range of carrier frequency, that is audio signal, we'll be using one more carrier, and we call that carrier as audio frequency carrier. Okay, so how do we define carrier? I told you that a carrier is a high frequency signal which could carry our signal from one place to another. When I say audio frequency carrier, this audio frequency is not a high frequency carrier. This audio frequency carrier, say my audio signal lies between, I told you, it lies between frequency ranges from 20 hertz to 20 kilohertz. I told you this thing. Okay, so this frequency is 20 hertz and this frequency is 20 kilohertz. So this is my lowest frequency and this is my highest frequency. Okay, and my audio signal lies between this entire range. When I talk about audio frequency carrier, means I'll be taking a single frequency, okay, in between the range of this audio signal frequency range. And I call that single frequency as audio frequency carrier. So this audio frequency carrier is a fixed frequency in the middle of the audio frequency band. Okay, and we will phase shift this constant frequency. Okay, this audio frequency carrier frequency has nothing to do with, you know, your carrier signal for modulation. This is just for phase shifting, and so that our scheme of generation of single sideband signal is, you can say, mature. Okay, so that way you need not get confused between audio frequency carrier and your actual carrier. That actual carrier, we call that as RF carrier. Okay, the meaning of RF is radio frequency. Radio frequency means high frequency. Okay, and audio frequency means your frequency in the audio range. Okay, that is low frequency. So you will very frequently come across this term AF and RF in your book also. So wherever you find term AF, AF means audio frequency, which is a low frequency. RF is your high frequency, means it is your radio frequency. Okay, so I hope all of you have understood that. So let us now move to third method. How does it look like? Fine. So this is our third method. So this third method is in a way identical to the phase shift method. Obviously, some changes have been made, but the second half of the third method is same as that of phase shift method. You see this one. This part is almost similar to that of your phase shift method, but this part, the initial part, it is different from your phase shift method. Okay, so that is one difference. Another difference is we are using audio frequency carrier for phase shifting. Okay, so we do not apply phase shifting on VM directly. We apply phase shifting on audio frequency generator. Okay, so let us see it's working now. So as I told you, the second part is identical to phase shift method, and then we'll be using audio frequency carrier. This is our audio frequency generator, which generates audio frequency carrier, and there is no phase shifting on the modulator. So first we will concentrate on this left hand side part. Okay, so let us see that. So we have balanced modulator 1, which requires two signal. One is your modulating signal and another is carrier. Okay, so in the first half we are using modulating signal, and the carrier is not the RF carrier, we are using audio frequency carrier. So in the balanced modulator 1, it receives modulating signal directly and it receives audio frequency carrier after 90-degree phase shift. Okay, so for the simple mathematical analysis, we have taken our audio frequency as twice of sine omega naught t. We have taken this as 2 sine omega naught t. The coefficient 2 is taken so that due to trigonometry we get a term 1/2. So in order to remove that term, we are taking this as 2. You will be able to understand this thing in mathematical analysis also. Okay, but right now you simply concentrate on the concept part. In the balance modulator 1, we get modulating signal as it is and audio frequency carrier after 90-degree phase. So twice of sine omega naught t becomes twice of cos omega. Similarly, in balance modulator 2, again it gets your modulating signal frequencies as it is and also the audio frequency carrier as it is. So twice of sine omega naught t, twice of sine. Okay, so in this way your balance modulator 1 gets Vm and twice of cos omega naught t, and your balance modulator 2 gets Vm and twice of sine. Fine. So after we have obtained the outputs of two balance modulator 1 and balance modulator 2, we pass our signal through low pass filters. I'll tell you what does these low pass filter do for us. You will be able to understand this thing in the mathematical analysis on the next slide. So after we have done or after we have passed our signal through low pass filter, we use this second portion. Okay, so here what we do, we use balance modulator 3 and balance modulator 4. Okay, now here for balance modulator 3 and 4, we will be using our RF carrier. This is our RF carrier, actual carrier. Okay, so here one signal is coming from the input side and another RF carrier for the balance modulator 3, our carrier is 90-degree phase shifted, whereas for balance modulator 4, your carrier is provided as it is. Okay, and then we either add or subtract depending on our requirement, whether we require upper sideband signal or we require lower sideband signal. I hope all of you have been able to understand up to this point. And this thing will be further clarified in the next slide, where we will prove mathematically that how actually we get single sideband signal here. Okay, so let us now move forward. So this is our generation of SSB signal using third method. For your reference, I have included the block diagram that we saw in the previous slide also here. Okay, so now we analyze each and every block mathematically first. So let us see. First, we look at balance modulator 1. So we know balance modulator provides the multiplication of two signals. So at balance modulator 1, we get modulating signal as it is, which is nothing but capital Vm sine omega mt. Okay. So let us see how do we get that. And then we have audio frequency generator, which gives us 2 sine omega naught t, and it is 90-degree phase shift, which gives us 2 cos omega naught t. So we get the multiplication of this and multiplication of this. Okay, so here in this analysis, you have taken Vm as capital Vm sine omega mt, and capital Vm has been taken as 1. That's why it has not been shown here. So you see here that this is your modulating signal Vm sine omega mt, and this 2 times cos omega naught t, this is your 90-degree phase shifted signal, and we are using audio frequency generator. Fine. And we know that we have the terms sine omega t, cos omega t. So if you apply trigonometric identity, this is your sine A cos B, okay, which gives us cos A plus B plus cos A minus B. So if you apply that identity, you get this term, that is cos of omega m plus omega naught t plus cos of omega m minus omega naught t. And I hope you can see here, this omega naught is the audio frequency carrier. This one, not the RF frequency. Fine. So we have got the upper sideband and lower sideband, but these are not the upper sideband and lower sideband which we actually wanted. This will come in the second stage. Okay. So that was your output of balance modulator 1. So now let us move to output of balance modulator 2. So for balance modulator 2, what we have modulating signal as it is, and we have your audio frequency generator signal also as it is. So we have the multiplication of 2 sine omega naught t, and this is your sine omega mt. So the output of balance modulator M2 is nothing but 2 sine omega mt sine omega. So you have 2 sine A sine B. So if you apply trigonometric identity, you get cos of A minus B minus cos of A plus B. So as a result, you get cosine of omega m minus omega naught into t minus cosine of omega m plus omega. So this is the output of balance modulator 2, and this is the output of balance modulator 1. So we have got V1 and we have got V2. Now we pass V1 through low pass filter. Okay, what is the purpose of low pass filter? The low pass filter passes the low range of frequencies and it removes the high frequencies. Okay, so if you carefully observe in your output of M1, this is your low frequency which will be removed, and this is your this is your high frequency which will be removed, and this is low frequency which will be passed. Whereas in case of M2, this is your low frequency that will be passed through, and this is your high frequency which will be removed. So your output of low pass filter F1 is your sine of omega m minus omega naught. Fine. Similarly, your output of low pass filter F2 is your cosine of omega m minus omega naught into t. Fine. I hope all of you have been able to understand this. Fine. So then now we move to this one. So here, what we do, we have balance modulator 3. So in the balance modulator 3, we have as an input, one is V3 and another is 90-degree phase shifted your carrier frequency signal generator. Okay, so this carrier frequency generator, it is phase shifted by 90-degree, and that's why your 2 sine omega naught t becomes twice of cos omega naught t. Fine. So if you do that, if you apply the same concept of balance modulator, what do we get? We get the output of balance modulator 3. So here, what are the two terms? One is the term from low pass filter F1. So this is the term. This is multiplied with your twice of cos omega naught t. See, you have twice of cos omega naught t. In fact, let me tell you more clearly. There is a minor mistake in the figure that has been shown here. In this balance modulator 3 and balance modulator 4, this frequency will not be cos omega naught t, it will be cos omega ct. This will be also omega c. This will also be omega c. Okay, I told you now that in the first half, the frequencies which are there regarding carrier, those are Oreo frequency carrier generator frequency. Okay, whereas in the second half we have the actual RF carrier frequency, so it should be, you know, omega c, not omega naught. And you can see in the analysis that your RF carrier, when it is shifted by 90-degree phase, you get twice of cos omega ct. So you see, this is our carrier part, twice of cos omega ct, and this is our filter F1 out. Okay, so this is our output of balance modulator 3, that is V5. And we know the two frequencies are multiplied. Again, trigonometric identities we will apply. We have cosine multiplied with sine, or you can say 2 cos A sine B. Okay, and you already know those trigonometric identities. If you apply those identities, then you can see that you get sine of omega c, okay, plus omega m minus omega. Okay, so if you take this as, say, A and this as B, what do we get? Sine of A plus B minus sine of A minus B. Okay, so that's what we have got, sine of omega c plus omega m minus omega naught minus, okay, sine of omega C minus omega M minus omega T. Okay, so this is the output of your balanced modulator M3. Similarly, we get the output of balanced modulator M4, where we have the low pass filter F2 output, which is nothing but this one, cosine of omega M minus omega naught T. That is this one, cosine of omega M minus omega, multiplied with your carrier frequency generator, which is nothing but the same, twice of sine omega ct. This is twice of sine. So this is what do we get? 2 sine A cos B. So if you apply identity, what do we get? We get sine of omega C plus omega M minus omega naught T, and instead of minus sign we have plus sign here, sine of omega C minus omega M minus omega. Okay, so we get, this is how we get your V5 and V6. Fine. So now we have reached the situation, the similar situation as we saw in the phase shift method. Now we have V5 and V6. Okay, you look at these expressions carefully. Here we have, this is nothing but upper sideband. This is what? Lower side. This is also upper sideband. This is lower side. If we want upper sideband, we will add these two frequencies, these two terms, and these terms will be cancelled. And if you subtract these two expressions, what do you get? Then these terms will be added and these terms will be subtracted. Okay, so we can add V5, V6, or we can subtract them depending on whether we want upper sideband or lower side. Let us see that in the next slide. This is what we have finally obtained. So your output of M3, okay, is V5, okay, so which gives us this omega C plus and this minus sign you notice. Similarly, output of V6, we have a plus sign here. Okay, now the output of the adder. Output of adder could be by adding V6, V5 or subtracting V6, V5. Okay, so in one case, we will have these frequencies added together. If you add them directly, you get this upper sideband. Whereas if you subtract them, you get the lower sideband. Fine. As a result, we get the generation of single sideband signal by third method. And you can very easily see here in this block diagram that we didn't shift VM anywhere. We shifted single frequency only. Firstly, we shifted audio frequency and then we shifted the carrier frequency. So that way, whatever disadvantage we had with us in phase shift method, that disadvantage has been removed in the third method. I agree. The block diagram of third method is quite complex and quite, lengthy also as compared to your phase shift method, but we get advantage also. See students, if you want to incorporate more and more features, and if you want to make your system more and more perfect, complexity will definitely be increased. Okay, so if you want to keep your system simple, then complexity will be less. And if you want to make your system, efficient, then complexity will be more. So depending on whatever is our prime requirement, accordingly, we will use that particular circuit or particular block. Okay, so this is all about our single sideband signal using third method. Fine. So students, this is how we have been able to generate a single sideband signal using third method. So after this, now we move forward with our discussion. Okay. So now we are complete with our, amplitude modulation part or generation of AM signal part, where we have seen the generation of double sideband full carrier signal. We have seen the generation of double sideband suppressed carrier signal. We have also seen the generation of single sideband signal. Okay, one more form we had discussed, that was VSB, that is vestigial sideband modulation. And once you have understood single sideband generation, then vestigial sideband modulation is very simple thing, because we know that in single sideband we removed one sideband and we keep with us one sideband. Fine. Now in vestigial sideband we have complete one sideband and some part of another sideband. So just by using filter, we can add the vestige part, or we can obtain the vestigial sideband modulation. Okay, so by filter method we can obtain our vestigial sideband modulation. So that's why it didn't require much elaboration, and there is no need to exclusively cover VSB modulation. Fine. So that way we are done with our amplitude modulation part. Now we need to move to amplitude demodulation. See, I told you that the main objective of modulation was to take our signal from transmitter to receiver. So once we have done modulation, we have boarded our modulating signal onto the carrier and we get modulated signal. Okay, so now demodulation takes place at the receiver side. Okay, so what happens in demodulation? Our modulated signal, it goes at the input of demodulator. Fine. And our demodulator gives us back the original information, the signal. So whatever we did in modulation, the reverse of that is demodulation. And students, another name for demodulation is detection. So we can say that now we are going to discuss either AM demodulation or we are going to discuss AM detection. Means we are going to do the reverse process of what we have talked about in the previous few classes. Okay, so in case of demodulation, what we have your modulated signal. This was our modulated signal. This modulated signal is demodulated or is detected to get back original information signal. So now we are doing the reverse process. Okay, and I told you in the beginning itself that the biggest advantage of AM is its simplicity. Okay, and we have already seen that the generation of double sideband full carrier was obtained simply by multiplication of two signals. So that was the beauty of simplicity of amplitude modulation. So similarly, the demodulation part is also very simple in case of AM. Okay, so when we get back, our original information signal back, see what our aim is. As I told you that in case of communication, what we have two entities. One is your transmitter, okay, and another is your receiver. Fine, and we transmit modulated signal from transmitter to the receiver. Okay, your signal goes from here. Fine, so here you have modulated signal, this one. Okay, and in the channel, what we additionally add, we add noise. In fact, we do not add, it is the inherent characteristic of channel that noise is added. At the receiver, what do we get? We get modulated signal plus noise. Now, what is the job of receiver? The job of the receiver is, much more difficult as compared to transmitter. The job of the receiver is to remove noise. The job of the receiver is also to remove carrier, so that whatever information part is present in that modulated signal, that we can retrieve back. Okay, so right now we are not taking into consideration the noise part. We are assuming that noise has been removed. We have with us modulated signal. Okay, and now in modulated signal we have two things. We have carrier, okay, and we have the information. These two things are there in our modulated signal. So at demodulator or at detector, now our job is to remove carrier. and to get back the information. Fine. So that is the job of our demodulation or detection. So the circuit which is used for detection of AM or demodulation of AM, that is called envelope detector. Okay, and another name for that is diode detector. Okay, and very popularly it is known as envelope detector. Fine, and why do we call it as envelope? You know what is envelope? Envelope is something which covers or which envelopes something inside it. Okay, envelope is a cover. So if you look at this AM signal carefully, you can see that your carrier part has been enveloped in between your modulating signal. Okay, so these blue lines are the envelope, and these red lines, this is the carrier. So you can say that your carrier is enveloped in between your blue lines. Fine. And now what do we want? And these red lines, these are nothing but the carrier part, and the blue lines are nothing but the information part or your message signal part. Okay, and as I told you, what we want the low frequency signal back or our message signal back. We want to remove the carrier. Okay, so if we again look at this figure carefully, see, if you look at this diagram, here we want to remove this carrier part and we want to retrieve information. And where is the information? Information lies at the top of the carrier or at the bottom of the carrier, either on the of the sides. Okay, so it means we have to extract these blue lines by removing red lines. That is the job of envelope detector or diode detector. Fine. So this is your AM demodulation. I'll talk about its circuit in the next slide. Okay, just give me 2 minutes for that. Okay, now let me explain two more things before I conclude here. Okay, see, when I say that, here I have two things. One is your modulating signal and another is carrier. My carrier is what? Say I represent carrier with the C. My carrier is high frequency signal. Fine. And say I represent modulating signal or my message signal by M. My message is low frequency signal. Fine. And now I want to remove this high frequency signal and I want to keep low frequency signal. Fine. And obviously, I want some method with the help of which I can retrieve this thing. Okay, and my information is present on the top of this high frequency signal or at the bottom of this high frequency. Either of the two I can take. Okay, so my first job is to select whether my information signal is to be retrieved back from the top part or from the bottom part. And how can I do that? My top part is positive and my bottom part is negative. Fine. And if I want to select either positive or negative, the most simple device for that is a diode. We know that diode is a single side device which allows our signal to pass through in one direction. Okay, so if your diode is connected in this direction, or if your diode is forward biased, it will allow signal to pass through. If diode is reverse biased, it will not allow signal to pass through. Okay, so if I want only the positive part, I'll use a diode, and in that case, my rest of the signal will be clipped and only positive part will be left. I'll get this thing. I'll get such kind of, say this is my positive part and my carrier has been clipped. Okay, only positive part is left. Rest of the things are removed because of diode. This negative part, it has been removed. Okay, so obviously the first step that I want is diode to remove one of the side. either positive or negative. That's why its name is diode detector. Okay, so once we have removed one part, then what we want? We want to remove high frequency. We want to keep low frequency at the output. So means I want a low pass filter, which will allow my low frequency modulating signal to pass through and remove other things. So I simply need two things. One is diode and another is low pass filter. So if I have these two things, I get envelope detector or I get diode detector. Okay, so I hope the concept of envelope detector or diode detector is clear to all of you. Fine. So students, for today's class, I stop here. I'll talk about the circuit of diode detector or AM detector or envelope detector in the next class. And I ask you people to read about all these things and try to develop the concept that how envelope detector will be able to detect our signal back by using the things that I have put in front of you. Okay, so I stop here.